starting it off with the weekend talk series. And our first speaker is Parth Kapoor from MS16. He's an avid physicist, a guitarist, a blogger, and currently is doing his fifth year MS thesis with Dr. Arvinder Kaur Jessel, and he'll be talking about, he'll mention his work and his present. Oh, 1 minute. Yeah, so, excuse me. He'll start I invite Parth Kapoor to start the talk.
Okay. Am I audible?
Oh, yes. Yeah.
Begin. I will. Just a minute. Can you see the screen?
Oh, yes.
So, welcome everybody. Thank you for coming. And I'm sorry. So the thing, I cannot see the chat or any of the other participants while I'm sharing screen. So if something you're going to have to pick up, I think Bhas already said that questions will be.
Mr. Path, your screen is not visible.
One second.
It is visible.
It's visible. It's visible. Space, dark energy, and a open story. It's visible.
Okay, cool. So let us begin. Okay. So I'll just lay out what we're going to be talking about. I'll give a very brief description of cosmology. Go further, this is not going to be a very advanced talk. So, I mean, the seniors that are here, if you're expecting of general relativity and cosmology, that is not going to be happening. I'll give a very brief description of cosmology. I will introduce Einstein's field equations, which is what you get when you study general relativity and apply it to space-time. And I'll mention the expanding universe, and then we'll see how observations showed us that a static universe match up with the observations that we have from satellites. And then we'll finally talk about what fixes that problem, which is dark energy. It up in a dictionary, the definition of cosmology is that it's the study of the universe, its origins and dynamics, which is just how it evolves in time. The most fundamental assumptions that we work with, cosmological principle. And what it essentially says is that there are no special points or directions in the universe. No matter where you're standing and in which direction you are looking, the observations you make and the conclusions you make about the geometric properties of space-time are going to be the same. And this is obviously on a very, very large scale. So details like planets and stars, even galaxies, do not really matter. It's all considered to be smeared out in just one uniform blob. It's called a homogeneous and isotropic universe. Homogeneous being there being no special points, and isotropic meaning there being no special directions. The field equations, these are what Einstein gave us, and in any textbook you can find them relatively close to of where, I mean, after they have introduced a lot of differential geometry, which is what you need to study to get to these equations. So on the left-hand side, the two G's that we see, the small g is called the metric tensor and the capital G is called the Einstein tensor. And the left-hand side of this equation is really what the information it encapsulates is the geometric properties of space-time. and if there are any special wavy properties to it. And the right side, T mu nu, is called the energy momentum tensor or the stress energy tensor, depending on who you ask. And that encodes information about the distribution of matter and energy in space-time, and also its flux, how it moves through space-time. And what this equation gives us is essentially what the popular adage of general theory of relativity is that the presence of matter affects the shape of space-time, and that curvature is what we perceive as gravity. And so there is another assumption that we make here. Now, these matter and energy distributions that reside inside this energy momentum tensor, which for those of you who don't know, I mean, this is a second rank tensor and can be expressed as essentially a two-dimensional matrix. We can superimpose all of these different kinds of distributions that we have. There can be matter, there can be energy, and in matter in particular, there can be all types of particle fields, there can be tachyon fields, and the others that you generally find when you study field theory. But another assumption that we make at this point is that we assume this matter and energy density to be distributed as a, and all that assumption does is that it simplifies the form of our energy momentum tensor. If we are to look at it in the form of a two-dimensional matrix, what it does is that it gives us a diagonal matrix. And it really simplifies our equations because then, and we can just get them out of the equation. Because the Einstein field equations is not just this one equation that's on the screen. Values for mu and nu, which range from 0 to 3, you get a huge set of equations which are, let's say, specific to each direction. And coming back to these matter and energy distributions, each of these distributions are categorized by what is known as the equation of state parameter, which is represented by W. A better idea of what I mean by superposition, because I assume a lot of your first year students. So on the left, we can assume them to be a matter field and an energy field. And when it's literally just an addition. And when you do that, you get the distribution on the right. Now, I have shown them on the left as being spaced out, but you'll need to imagine them being at the same point in the on the z-axis and lying on the same plane, essentially. For matter and radiation in particular, the W, the equation of state parameter, which is what categorizes these distributions, W is equal to 0 for matter and -1/3 for radiation. Reason for this is slightly involved. We'll have to go into more details about the stress energy tensor, which is not something I want to do right now. Skip that and instead talk about we currently are living in a matter-dominated universe. And what I mean by that is we don't know what the distribution was when the universe started near the Big Bang. Now that radiation has way as the universe has expanded. I am assuming everybody at this point knows from popular science books or videos that you must have watched that the universe is expanding. Expansion happens if you assume just a 1 by 1 by 1 cube. If there are 10 matter particles in it and that cube expands to double its size, the matter density is going to become 1/8 of the original amount. But radiation actually goes through another effect. As the universe expands, the source of this radiation actually is also shifting away. And so individual photons, in which case they actually lose more energy than they would have if they were redshifted. So that actually introduces another power to the 1 by r cube term that we saw for matter. And just doubling up in size, instead of becoming 1/8, radiation becomes 1/16. So as the universe expands, radiation actually dilutes out faster. And that is the reason that we see around us there to be a matter dominated universe.
Parth, if I'm sorry if I'm interrupting, but I just wanted to know this omega term that you introduced. Where does that feature in the Einstein's field equation?
This W?
Yeah, yes, this W over here.
Yeah. So when you actually write out the energy momentum tensor in the perfect fluid distribution, it becomes diagonal rho PPP, which is energy density, pressure, pressure, pressure in the three directions. And the equation of state parameter is basically what links those two terms. So for matter, we say that rho is equal, I mean, for anything, the equation of state parameter, how it factors into it is we say that rho is equal to WP. And for matter in particular, we model it as a pressureless dust. So P becomes zero. It might be the other way around. It might be P is equal to W rho, in which case, when you put matter is equal to zero, P is equal to zero, W has to become zero, otherwise the equation wouldn't make sense.
Okay. Yeah, thanks. Yeah.
Okay, so let's talk about the expanding universe.
I have another doubt regarding that the omega term, the state parameter.
Yeah.
If it's the ratio of pressure by density, shouldn't it be positive for radiation?
Not exactly, because in the energy momentum tensor, you can have negative energy density as well. And also in the, when you actually write out the tensor, it's not just rho P, 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 it's rho minus P, minus P, minus P.
Okay, so the pressure is, so
So,
either
I
the
mean,
pressure is negative or the density is negative.
it doesn't really matter. It depends on your, what do you call it? Convention. You can define it by convention. It doesn't really matter that much.
Okay.
Yeah. Okay. So any other questions? Okay. So expanding universe. Einstein was not very comfortable with this idea universe, even though it is what the equations guided him towards. But I think at some point in the 20th century, Hubble used his telescope and he proved beyond a doubt that faraway galaxies are actually moving away from us. On Earth, there's this thing known as the Hubble parameter, which essentially holds the information about how fast exactly the universe is expanding. Now, there are two versions of it. There is h naught and h as a function of the redshift. The value of the Hubble parameter at current epoch, which is at the current in the universe's history, and hz is the apparent value of it. It is the value measure as a function of distance, which is what redshift is for cosmologists. To get that point across slightly better, I have these two images, which are really, really amazing. If you look at this first quadrant over here, assume all of these points to be galaxies. Now, the galaxies in gray are at some time t equal to 0, and then as time progresses, they expand to this blue state. And then you can see has increased. Now, it's important to realize that nothing is actually moving away from one particular point. It's just expanding as a whole. Consider two special points like they have in this yellow and red galaxies over here, and then track them. Choose that yellow point where you are going to now make your measurements from, and you just overlap the yellow galaxies in at the t plus delta t time and t is equal to 0 time. Then you can see why it would be apparent to us as if everything would be moving away from us. Thing with any other galaxy, as they've done over here with this red one, and then it appears that it's moving away from that particular galaxy. We're not really at the center of the universe, if you think about it. Now let's look at some of the observations of that Hubble had made. I mean, these are not his original observations, but observations of the Hubble parameter. I don't remember when this data is from. I'm assuming it's from some point 15. So the purple points that you see on this plot are the actual values of the Hubble parameter. Only consider there to be matter and radiation in the universe, and you put that into the mathematical form for the Hubble parameter. What you end up with is this blue line over here. And as we can see, the Hubble parameter actually just eventually asymptotically goes to 0. So the expansion of the universe just stops matter and radiation. But that is not what the observations tell us. So to fix that, what cosmologists did was they just took the equation for the Hubble parameter, and on top of matter and radiation, they just added another density. This was purely a mathematical addition to this formulation of the Hubble parameter. And they just took whatever form seemed most relevant to them and whatever form seemed to give them the right answer. And when you actually put that extra energy density, you see that, I haven't shown it here, but the that you get when you plot it out, it actually matches closely with the observations. And that mathematical just energy density that we have added on is what is known as dark energy. Dark because we don't really know what its origin is. Candidate models that are available to us. One of them is lambda CDM, where we just say that dark energy, the W for it is simply a constant and it is equal to -1. There is also WCDM, which says also that the equation of state parameter for dark energy is a constant, but its value is different from 1. So far, I have tried it with different data sets. That I have gotten is around -8.9 for one data set and -9.2 or something from another data set. Close to -1, but it still gives a better fit to the data. And there's quintessence, there's tachyon field, there are neutrino fields, and people have been working on all of these for a very long time. That all of these models, they come with a set of free parameters, because we don't really know what the actual origin of dark energy is. And so all of these, the equations for the equation of state parameter have these free parameters that we don't know the values of. This is a problem. There are so many of these candidates, and the free parameters can be tuned to fit any data. So we don't really know which one is correct. We can fit all of these models that are available, and there are probably 20 or 30 more of these. Which one is the correct one? So that is what my work has been in so far. I've been doing computer simulations. We use Bayesian analysis to constrain the values of some of these free parameters based on different models. Does not give us a method to decide which one of them is correct. So currently, what most recently my work has been on is we've been working on a non-parametric approach where we just say that, look, here's the data, and we're just going to assume that W is some function that we do not know. But so there's this technique used in machine learning, which is known as Gaussian processes, which is where you just take a bunch of random functions, fit them to the data using Bayesian analysis, and just use these random functions as your form for W or as your form for one of the observables. And then what the plan is, after I have done that, to then compare those with the existing models and the results that you get with existing models, and see models match up to what you get when you go for a non-parametric approach to the equation of state parameter.
Excuse me.
Yeah, that has been it. I mean, that was the entire presentation. So I'm open to questions now.
Okay. let me ask this question. Are you considering the models in which dark energy and dark matter are interacting, or are you just treating them as some separate components?
No, so all of these components are always treated as non-interacting because that's how the superposition works, right? You've just added them onto each other. That's it.
But I have read about some models in which the people are actually considering that the dark matter is formed from dark energy,
Okay.
just like matter is formed from energy, and the data is quite a good fit.
Okay. I mean, I don't know about that because dark matter by definition is supposed to be non-interacting. So I haven't read any such work yet,
Actually,
but I
dark
don't.
matter is not interacting with our sector, but there are
Yeah.
interactions within dark sector which we can discuss, like
I don't know what you mean by dark sector, but sure. I
dark energy
mean,
and dark matter. They constitute the dark
okay.
sector.
Okay. I'm sure there must be some work in that direction. Yeah.
But
Actually,
Yeah.
I just had this question on when you were mentioning about these ways of, let's say, the whole idea is to, there are so many models and you have to figure out which one doesn't work out or
Yeah.
even
Yeah.
falsify. So when you meant you're adding this to say
Yeah.
tensor, in this is with regard to the Einstein field equation? Is
I
it
don't understand. What do you mean?
like, what do you mean when you're saying you're going to add these energy tensor? I don't know. That's what I heard, or maybe I understood that wrong.
What I'm
This
saying is
lambda
that
CDM model or any of these models, what do you add it to? In some sense.
yeah. So the thing is, when you actually look at the form for W, I should have probably included that equation. Let me see if I can find it somewhere. So I
I
mean, the
think
idea
it's
behind, yeah, you were saying something.
yeah. I think it's the equation containing entropy now.
No.
Okay.
Yeah. No, the idea is that all of these matter densities can be modeled as a distribution, right? And there is, and they can be because we are assuming it to be a perfect fluid because it's all smeared out and we assume homogeneity and isotropy. We just have a diagonal form of the energy momentum tensor, but we need to get rid of one of the variables essentially to simplify our equations further. So the equation of state parameter links p and rho. Right now, but what exactly that dependence is between the pressure and rho and on the form of W. Like I said, W is equal to 0. But for dark energy, there are several different models. If you're working with lambda CDM, that model, that W is just equal to -1. So there would be a negative there would be a negative pressure or a negative energy density to however much matter. I'm saying matter, but whatever energy density there is, it would have a negative pressure. And then
Just for my clarity, from what you have told and explained, this is what I understand. Like, you have this T mu nu, say
yeah,
tensor, you have this
yeah,
parameter called omega sitting there, in some sense, and this parameter. There are other dependencies with, with pressure and matter and stuff, and the idea is to figure out what omega is. In any sense,
the idea is to figure out the form for omega. Yes.
form for omega. Okay, I see.
Um, Let me stop.
Thanks. Okay, fine.
Well,
In
I just
the okay,
yeah, go ahead.
so I was asking, what are the limitations you are going to put for the um, brute force kind of finding function method? Like for finding functions, you are just using random functions, right?
So, have you studied about Gaussian processes?
Not yet.
Okay. So, Gaussian processes is essentially a method where you can use the data, and what it does is it generates. Actually, you know what? Let me just open my project page, and I can show you really pretty graphs. If you would just give me a minute. Thesis. Yeah, let me share my screen. Right. So can you see this graph on screen?
Yeah.
Yes.
Okay. So these are the random functions that you would generate. And this is, I have just taken this to be simulated data. So this is just sine of x. And these black points are the 6 points of sine, just 6 values of sine that I've taken at different values of x. And what Gaussian processes gives us is that you would begin not with this, but you would begin with GP generating prior, something like this, where it's just entirely random. There is no structure to this, right? If you actually put in the data, and there's a lot of mathematics behind it and a lot of matrix manipulation, but when you do that and when you analysis to that initial mess that you have, you can see that all of these functions, they get cinched in to the point wherever we have data points. So it's sort of how do I say it? It sort of closes in to wherever the data is, and it picks out, it favors those functions which give the least amount of error when faced with that data.
Okay.
Does that answer your
Yeah.
question?
Yeah.
As for Roshan's question, I think it should be somewhere here once again. Does anybody have any other questions?
I just had this, I don't know, comment on seeing, let's say that matrix equation you'd written, say G is equal to G plus metric is equal to, say, the stress tensor.
Yeah.
Let us say T mu nu is not diagonal, but we could it, right? In some sense, like, then what would be the interpretation?
You can't always diagonalize it, but there's also when you diagonalize it, you do not have the guarantee that the three pressure terms are going to be the same.
All right. Okay.
Yeah. So that is really what we are looking for. We want those three to be the same so that they can, I mean, because you're assuming there to be no special directions, right? Okay.
Yeah.
I have found the report that I wrote. Let me see if I can find the relevant. Okay, I found the relevant page. Can you see the PDF in front of you?
Yes, we can.
Yes.
So if you look here, when you apply energy conservation, this is the form for the this is the equation that you get when you say del mu T mu 0 is equal to 0, which is conservation condition. Then you get this form, and A dot over A is simply H. That is how you define H. But you need some way to relate P and rho over here, and that is where you introduce this omega. You simplify this differential equation, you get is this one, which is equation number 4, which you can once again, if you boil it down to essentially the energy density being dependent on A, which is the scale factor raised to this particular power. Really where W fits into the energy momentum tensor. Now, when you take the case of matter, you say W is equal to 0, and you see that the energy density falls off as a cube law, inverse cube law. What I said earlier, because matter, as the volume element expands, matter density gets diluted. But and only people who are in their third year right now would probably understand this equation. I'm sorry for the first years. Look at radiation. You actually work with Maxwell's equations in tensor form. When you apply, I forget the name of that condition, but there is a particular condition where if you apply the perfect fluid tensor, you end up with this particular equation. Then you can essentially get a form for W from here as well, which is over here, it's just mathematical. But if you want to look at it physically, it's the expansion, which reduces the actual number density of photons. But because of the expansion, there is also a redshift, which then further reduces the energy. And
In this document, you have written the state parameter for radiation as positive 1/3. In the slides, it was negative 1/3.
oh, that's probably a mistake then.
Yeah, in the slides, I had asked that question, right? That how can the pressure and density of radiation be negative?
Okay, that was probably a mistake on my part. But what I've written here as positive. Oh, right. You're saying that in the presentation it was negative.
Yeah.
Probably a mistake.
And I had another question.
Yeah.
In the starting, you had mentioned that the universe is homogeneous and isotropic, right? Uh,
Yeah.
but I have read some theories that consider anisotropic universes.
Okay.
So, like, does that come in your, like, do you consider those things also while in your
I'm
research?
sure. See, the thing is that you can always look at these things. You can always remove assumptions from your models, right? One by one, if you want to get more and more accurate results. But there is a point at which, if you, no matter how much you have increased the complexity of your model, the results you get don't really change much, and that is what you get even if with the isotropic universe. That even if you remove that condition, the change that you find in your results isn't really appreciable enough for you to actually justify removing that condition. As a theoretical, I mean, out of interest, sure, it's quite interesting to maybe look at it, but yeah, it's not really justified from a from a observation point of view.
Oh, okay.
Oh, don't worry about tensors. Who's asking? Um, yeah, I mean, yeah, whatever Sahil Shah says, it's a glorified matrix for now. Tensor, a first rank tensor is a one-dimensional matrix, and a second rank tensor is a two-dimensional matrix for now. No, because going into tensors is a whole other business. That's like a 4-hour lecture series. Any other questions?
I had a question that taking Wm equals 0 comes from an equation, or we take it to simplify our equations only?
So Wm equals to 0 comes from the fact that we assume the composition of matter in the universe to be a pressureless dust. It's an assumption which simplifies our equations.
Okay, it's just a simplification for our equations.
It is a simplification. You could have taken it to be, once again, another more complicated form, but it doesn't really help that much.
Okay, thank you.
Yeah.
Do you require this omega as some function of something? Why can't we just use the numbers we have in both sides?
What do you mean?
Like we have this h of omega plot, right?
Yeah.
Is, let's say we don't know the function. All I have is these numerical points. Is there some way to solve, use these points, quantities? I don't know.
Yeah, that's what the non-parametric form would be. That's what I'm doing right now.
Okay.
Because over there you don't take it to be any specific parameterization for W. The points, you form a function which fits those points well. And then you just use that. But the thing is, it doesn't really answer any questions. All it gives you is a function which is fit to the data. Asks you, like, okay, from your research, what have you found the origin of dark energy to be? You cannot say anything.
Okay. Thanks. Yeah.
Is that it?
One final doubt. Based on your work till now,
Yeah.
have you been able to rule out any model?
No, because I'm yet to complete the code for Gaussian processes. What I showed you was just with simulated data, but the code needs some tweaking to actually work with actual astronomical observations.
Okay, and you are using MCMC,
Yeah,
Markov,
that's Markov chain Monte
Markov
Carlo.
chain model.
Yeah.
Let me guess, Python EMC module.
No, I write my own code. It's C.
Okay, okay, thank you.
So I suppose that wraps it up. Thank you, Parth,
Yeah.
for the talk, and so I guess all of you enjoyed the talk. So,
Yeah, I hope so. Yep.
so, yeah,
Goodbye.
bye, guys. Thank you for joining us.
Yeah.